Okay, good morning, guys. Assalamu alaikum. Welcome back to Inspired Teens, grade 12 maths after a long break. Hope you guys are keen to be back. Okay, so before we get started, please can you guys just confirm, as usual, that you guys can hear me clearly, that you can see my screen, you can see me as well as on YouTube. If you guys don't mind, could you please just let me know, confirm with me? You can't hear. I'm not sure you can't, because they can hear me on Zoom. YouTube should be fine. Just double check, refresh the page or unmute the chat. But it should be working just fine. Okay, but nevertheless, let's get started, right? So last time we ended on functions. I think we did up until doing intervals with functions. Okay, so yeah, if you guys don't remember what we did or you need a refresh, you can always rewatch the video. I hope that you guys looked at those questions, and I trust that you guys are competent enough to attempt them. I think there's memos for every question. If there's no memos for any questions, just let me know. But yeah, okay, so go through those if you haven't already. And now we're going to start inverse functions, which is actually the grade 12 part of functions. Okay. So let's have a read here. It says the inverse of a function. The inverse of a function shows that the symmetry is the symmetry if a graph is a mirror image of the curve around a specific line. The inverse of a function is the symmetry of a graph about the y is equal to x line. So the y is equal to x line is a line that looks something like this. Okay, and why is it called the y is equal to x line? Simply because for every y value, it has the exact same x value. So if we have to consider an x value of 1 here, okay, the corresponding y value is 1 as well. Okay, and the same thing applies for 2 and 3 and so on. Okay, so that's what's called the y is equal to x value, because literally the y value is equal to the x value at every single point on this graph. Okay, so when we talk about a reflection about the y is equal to x line, y is equal to x line, we are talking about a reflection upon this line. Okay, so for example, if we have to have something that looks like this, for example, let's just say, okay, its reflection on the other side, okay, if this is a function, its reflection on the other side would look something like this. Okay, more or less, not perfect, but more or less. Okay, so yes, it's like you have a mirrored line. Okay, or if you have to have a page and you have to fold it on the dotted line, then these two graphs, the green and the orange graphs, they would touch each other. Okay, so that's what an inverse function basically is. It's the original function reflected about the y is equal to x line. Okay, so we have some steps here on how to determine the inverse function. We'll do it practically as well. But it says write in standard form, switch x and y, and make y the subject of the formula. If you've already done inverse, this might sound familiar to you. Before we go through this, let's just go through an example of how to follow those 3 steps, okay? So we're going to talk about the inverse of a linear function, okay? So remember, a linear function is for a straight line graph. Straight line graph. Okay, and the straight line graph, remember, has the formula y is equal to mx plus c, again, where m is the gradient and c is the y-intercept, okay? So if we have an example that f of x, okay, f of x is equal to negative 3x minus 2. So this is an example of a linear function, okay? And now they say find the f of minus 1. F of minus 1, whenever you see f of minus 1, remember that this is the inverse. Okay, you'll see later you have f prime, which is a little apostrophe. This indicates derivative. Okay, so just don't confuse the two. When it has a negative 1, it represents the inverse. When it has this apostrophe, it represents the derivative, which you guys will learn. I think maybe some of you may have started it, but you guys will learn it whenever you do calculus. Okay, so yes, they want us to find the inverse of f of x. So we have f of x. They want us to find the inverse of f of x. So let's just have a look quickly at these three steps. Write in standard form, switch x and y, and make y the subject of the formula. Okay, so let's go back to the question. Write in standard form. Okay, so it's already written in standard form, so we can rewrite it. We can say that y, instead of having f of x is equal to negative 3x minus 2, let's write it with y. So we have it in standard form, y is equal to negative 3x minus 2. Use that. Y is equal to negative 3x minus 2. Okay, so once we have written it in standard form, they then want us to swap x and y. So that simply means that wherever you have y, you're going to replace it with x. So you're going to have x is equal to negative 3. Wherever you have x, you're going to have y. So negative 3y minus 2. Okay, so x is equal to negative 3y minus 2. Then the final step is to isolate y, or to make y the subject of the formula. So basically just to leave y alone, okay, to write everything in terms of y. So in that case, I need to get rid of everything that's sort of attached to the y. Firstly, I can take the 2 to the other side. So I can have x plus 2, because I take it over to the other side, is equal to negative 3y. Okay. Thereafter, I can divide, because this 3 is here, I can divide everything by negative 3 to get rid of this 3. Okay. Once I do that, I am indeed left with x plus 2 over negative 3, which is equal to y. Okay, I can simplify this further. Let's just create some space. I can simplify this further, okay, by putting each term in the numerator separately with the denominator. And that's what I'm going to do. So x over negative 3 and 2 over negative 3. So because we're dividing by negative, it actually changes to negative x over 3. And then 2 over negative 3 becomes negative 2 over 3. Okay, I can write y on the side also. It doesn't really matter. Okay, I'm just swapping it, not taking it over to the other side. And if I want to simplify it a little bit more, I can express this guy as, with a coefficient to express the gradient, negative 1 over 3x. Minus 2 over 3. Okay, and that's the most simplified version of it. So ideally, you don't want to leave it in this format, because it's in a straight line. You want to try and get it into the y is equal to mx plus c format. Okay, that's ideal. Okay, so I hope that makes sense. Okay, if we have to look at a visual representation of what an inverse would look like. So we have this straight line function, a straight line graph. Does it represent this graph? No, I don't think it does. Okay, it's a different graph, but it doesn't really matter. So so just to get a visual understanding of what an inverse graph would look like, we can try and draw this inverse graph for the straight line function, right? So we did the equation. We went from the standard equation, or f of x, to the equation of its inverse, okay, which is that. Now we can just do a little diagram of it. So again, you have your straight line function, you have your y is equal to x line. Okay, so all you need to do is reflect it about the y is equal to x line, which actually sometimes sounds simpler than it is. It can get a little bit confusing at times. But the way I like to do it is to reflect it piece by piece. Okay, so however you want to, I want to reflect this one first, then I'll reflect this side. Okay, so I can do them separately piece by piece. Let's get rid of that. Okay. And all I need to do is, you can sort of tilt your page, or however you're comfortable doing it, and then reflect each one. This is actually confusing. But if I draw a dot here, Okay, I can see that that sort of goes top left. So I take this as its reflection. Obviously, you'll be using a ruler, something like that. Okay, and then I can see that this one is going slightly down. So of course I need to continue the straight line. So this would continue straight. So if the first half is drawn sort of correct, then your second half should be good as well. Okay, so something like that. Okay, just estimating what it would look like if you just solely relying on the reflection about the y is equal to x line. Okay, there is actually a more accurate way that we can do this, and we can refer to this little table, okay, where we have some differences, key differences that are really important for you to note and actually make answering these type of questions a bit easier, okay, and your understanding of functions a bit more clear, or sorry, inverse functions. So what I've noted here are the differences between the regular function and the inverse function, okay. So the first thing we're going to talk about is any coordinate. Okay, so if we have any coordinate where we have an x and a y value, any coordinate, more like actually any and every coordinate will follow the same behavior. Any and every coordinate follows the same behavior. So if we have a with the coordinates 4 and -3, okay, its image, they refer to this as the image of a. The image of a is basically the same coordinate, okay, but on the inverse function. So the image of a prime in this case, okay, would basically flip its values. So the x value becomes the y value and the y value becomes the x value. So here you'll see we have 4 and -3 for the regular function. And for the inverse, you have -3 and 4. So the x and the y value flip. And this is true for every and any coordinate going from the regular function to the inverse function and vice versa. Okay, so you should also understand that if you have a coordinate on the inverse, okay, its corresponding coordinate on the regular function is you flip the coordinate. So the x becomes the y becomes the x. Okay, hope that makes sense. So yeah, they refer to that as the image of a at times. So you need to understand it. Please be aware that the image of a could be on the regular function or the inverse. Okay, it doesn't matter as long as it's the opposite. What I mean by that is if I have a coordinate here, let's just call it, what can this be? -5 and 3. Okay, its image, so this is on the regular function. The image of this coordinate, okay, would be on the inverse and would be 3 and -5. I know that. That's always true. So I can also just simply plot 3 and -5. So 3 maybe is like somewhere here, and then -5 is like somewhere there, right? So you can plot that coordinate, and it would be, if you have to see, it would be something like this. Obviously, it's not drawn to scale, so it's not perfect, but it would look something like that. And you can kind of see that these two are reflections about the y is equal to x line as well. Okay, those separate individual coordinates are a reflection about the y is equal to x line as well. Okay, so I hope that makes sense. Every coordinate flips, okay? And we can further note that the y-intercept of the regular function becomes the x-intercept of the inverse. So let's clarify that a little bit. Okay, so for example, if the y-intercept is y is equal to 3, okay, or it has coordinates 0 and 3, because remember the y-intercept, all the x coordinates are 0. The x coordinate is always 0. So if our y-intercept is y is equal to 3 and its coordinate is 0 and 3, then the x-intercept on the inverse will have the coordinates 3 and 0. And the x-intercept would be x is equal to 3. Okay, so I hope that makes sense. Okay, so basically the y-intercept becomes the x-intercept. That doesn't mean that you're going to say y is equal to 3 and then y is equal to 3 as well. No, x-intercept needs an x coordinate, so it becomes 3 and 0 instead of 0 and 3. Then we have, again, like vice versa, the x-intercept becomes the y-intercept. So if the x-intercept had to have a coordinate of 2, it would have this coordinate 2 and 0. Then the y-intercept on the inverse would have a y coordinate of 2, and its coordinates would be 0 and 2. Okay, then we talk about the domain becoming the range. Okay, so whatever the domain of the regular function was, the range of the inverse would be the same. Okay, so let's do an example. If the domain of the regular is x is an element of real numbers, then the range of the inverse is y is an element of real numbers. Okay, so again, because they say the same, don't make the mistake of saying, oh, the domain of the regular is x is an element of real numbers, so the range must also be x is an element of real numbers. No, it needs to change to y because range contains y values. Okay, so just keep that in mind. And of course, vice versa. So the range becomes the domain. So if the range, for example, is y is less than or equal to -3, then the domain would be x is less than or equal to -3. Remember, domain is for x values, range is for y values, always, right? Then we talk about turning points in the case of parabola. So the xTP actually becomes the yTP. So if the xTP is x is equal to 1, then the yTP of the inverse is y is equal to 1. Okay, please note that these work both ways. Okay, so whether you know the coordinate on the inverse, you should be able to get the coordinate on the regular. And whether you know and if you know the coordinate on the regular function, you should be able to get the coordinate on the inverse. Okay, so it works both ways. Okay, so let's move on, right? So we said that there's an easier way to plot it. So remember, the y-intercept becomes the x-intercept and the x-intercept becomes the y-intercept respectively. So let's have a look at that, right? Let's get rid of this. Let's see how we can now plot this graph using that information. Okay, so here we have our that same function that we're dealing with, that linear function, and we have, let's look at the x-intercept. The x-intercept is -2. So on our inverse, the y-intercept should be -2. On our inverse, the y-intercept should be -2. So I go to my y-axis and I plot a y-intercept of -2. And this should be a point on our inverse graph. Then if I look at the regular function, the blue graph, and if I look at its y-intercept, its y-intercept is -3. Since the regular function's y-intercept is -3, the inverse's x-intercept should be -3. Okay, it might be a little bit confusing, but you'll get used to it really quickly, right? So it flips. So the x-intercept of regular function becomes the y-intercept of inverse, and the y-intercept of regular function becomes x-intercept of inverse. Okay, so it sort of needs to pass through all of this. Let's just see, because the scale is a bit bad. Let's just take this a bit more down, and hopefully we can plot a straight line. Should be okay. Let's plot it. So we can now more accurately, obviously, when you have it drawn to scale, then it's way better. Something like that. Let's see if we can move it down. Okay, there we go. Something like that. That kind of looks like a straight line. Okay, so there we go. It looks something like this. Okay, and that looks maybe slightly more accurate than our previous one, but when you're drawing it to scale, it's going to be 100% accurate using the information that we just learned. Okay, let's move on. Okay, so now that we've done the basics of inverse, okay, we're going to speed it up a bit just to finish the inverse of the rest of the different kinds of functions. Let's talk about one thing first, though, called the vertical line test. What is the vertical line test? It says in order for a graph to be a function, it needs to pass the vertical line test. Okay, so in order for a graph to be considered a function, it needs to pass the vertical line test. For every x value, there needs to be only one corresponding y value. Okay, so yes, it's a vertical line. When you pass a vertical line through a graph, it basically can only touch the graph at one point in order for it to be considered a function. For example, if we look at this graph, it's a parabola graph. No matter where I pass a vertical line through, it only touches at one singular coordinate on this graph. Therefore, we can consider this graph a function. Okay. Again, how do you prove that it's a function? Through the vertical line test. If it passes the vertical line test, meaning when you draw a vertical line through the graph, at any point, it should only touch the graph at one point. Okay. Well, what does an example of failing vertical line test look like? Like this. When I pass a vertical line through any point, okay, if it fails the vertical line test once, it's not a function. Okay, so here we go. When I pass a vertical line through it, it's touching the graph at 2 points, meaning this graph is not a function. Okay, so let's look at the technical explanation. It says for every x value, there needs to be only one corresponding y value, and that kind of makes sense if you think of it, right? Here, our x value is, let's just give it a number. Let's just say it's 2. Okay, if the x value there is 2, how many corresponding y values does it have? It has this one. And it has this one. Okay, so it has 2 corresponding y values. So it's not a function. In order for it to be a function, every x value, so for one x value, you should have only one corresponding y value, like in this case, where we have x value, y value, just one. Okay, so just keep that in mind. Really simple. If they ask if something's not a function, we'll give a reason it's not a function. You can say, you can obviously analyze it and you can draw a vertical line through it to test if it's a function. If it fails, you will say this is not a function because it fails vertical line test. If it passes, then you will say this is a function because it passed the vertical line test. Alternatively, you could even add, for every x value, there is only one corresponding y value, or for every x value, there is more than one, or you can say for x, for an x value, there is more than one corresponding y value, okay, whichever one you need to explain. Okay, let's have a look at the next example. We're going to talk about inverse of parabola. So the most basic formula for a parabola function is y is equal to ax squared. Okay, so you have to know the inverse of y is equal to ax squared. So let's do it through an example. F of x is equal to 3x squared. F of x is equal to 3x squared. Find f of minus 1, which is the inverse of f. Okay, so we follow the same steps. We write it out in standard form. Y is equal to 3x squared. We then swap x and y. So wherever we have y, we write x. And wherever we have x, we write y. So x is equal to 3y squared. And now we have to try and leave y alone. So I can divide both sides by 3. So I have x over 3 is equal to y squared. I can thereafter, because y has a square to it, I need to get rid of it. I can square root both sides. Okay, and when I square root both sides, I'm going to take y over. I'm not taking it over technically. I'm just swapping. I'm just swapping the two. Instead of writing y on the right and square root x over 3 on the left, I'm just writing y on the left and square root x over 3 on the right. It's like having, for example, something like a is equal to b is the same thing as b is equal to a. Okay, that's what I'm doing. Yeah. Okay. So now I have y is equal to, when you take the square root, you get a plus minus square root x over 3. Okay, and that's the answer to the formula of the inverse, okay, the equation of the inverse of this parabola 3x squared. Okay, so let us draw it. Okay. Okay, so okay, we'll discuss this plus minus in a second. Let's draw it first, and then we discuss the plus minus for those of you who are wondering, like, why do we have plus minus and how does that work in terms of the graph? Okay, so let's have a look at it. We have our y is equal to x line going across, okay? And we have this parabola graph, okay? We can maybe perhaps say that this represents y is equal to 3x squared. And then we can draw the inverse of it, okay? So firstly, I want to reflect this about the y is equal to x line. So again, I can do it part by part if I want. The more, like, if you get some practice in it, you'll be able to do it quicker. So I'm going to do this part, and I'm going to do this part. Then I can do that part. Okay, so when I reflect this first part, I can draw a dot where it touches, and then I can see, okay, it goes that way. So I can draw it to reflect it. I can draw a line that looks something like this. Okay, then I can have a look at this part, and I can, in order to reflect it, I can just simply complete the shape, which is gonna look something like that. Okay, and then finally I can do this last part, which is gonna look something like that. Okay, so obviously not perfect, but somewhat looks like the function, right? So that's what a reflection of the parabola graph would look like. Now, if you notice, if we have to do a vertical line test for this, for the inverse of this parabola, if we have to do a vertical line test for the inverse of this parabola, you will notice that it fails the vertical line test, okay? Which basically means that the inverse of parabola is not a function. The inverse of parabola is not a function. That's why you will notice, okay, you will notice that certain questions, when you deal with parabola, they will restrict the graph, okay? So what does that mean? Let's have a look at this, okay? We have an example of y is equal to 3x squared, but the restriction is that x is greater than 0. This is the restriction that they've given us. X is greater than 0, and I've actually drawn it in where we have the parabola graph of y is equal to 3x squared, where x is greater than 0. So the only part that's drawn, remember, this is the y-axis, and this is the x-axis, and everything to the right of the y-axis is where x is greater than 0. Okay, and everything to the left is where x is less than 0. So we didn't draw anything on the left, we only drew the parts on the right. Okay, so the reason we do this, if we have to look at the reflection of this graph, we will see that it looks like this. Okay, something like that. Again, it's not perfect. I'm no artist. Okay, but the reflection of this graph specifically, so again, it's a parabola, but with a restriction. So y is equal to 3x squared, but x is greater than 0, and its inverse is only half of this. So if you have to sort of maybe turn sideways, okay, you'll see that if we had to complete the rest of it, it would look something like this. Okay, that's not great, but when is my drawing ever great? Okay, so the complete inverse of the parabola would look like that, but the reason we restrict it is for this very reason, that the inverse, if we have to draw the whole inverse, it is not a function because it would fail the vertical line test. So for that specific reason, oftentimes you will see that we restrict. The question would actually deal with a restricted version of parabola, because when we inverse that parabola, it would be a function. So if we have to do vertical line test for this this pink graph, which is our inverse, it does not fail vertical line test anymore, and it is now therefore a function. Okay, so we restrict it each time. So what happens if we do y is equal to 3x squared? Okay, and actually, by the way, that's why we get the plus and minus. Okay, so plus and minus root x over 3. So in this case, because here actually for the regular function, y is equal to 3x squared, x is greater than 0. Here we have y is equal to root x over 3, and it's actually positive. Okay, it's the positive root x over 3, and of course you can see that y is positive. It also, its restriction is that y is greater than, we can actually say or equal to 0 to just include that point because we drew it. So for this one, x is greater than or equal to 0, and you can see it follows that same understanding for our normal function to inverse, where everything flips from x to y, and then the x value becomes the y value, and the x-intercept becomes the y-intercept, and the y-intercept becomes the x-intercept, and the x-TP becomes the y-TP, and so on. Here we have the restriction for the regular function being x is greater than 0, and in turn that becomes y is greater than 0 for the restriction of the inverse. And you'll notice that this pink graph only contains positive y values, again above the x-axis, where values of y are greater than or equal to 0. Okay, so just keep that in mind. And yes, there we go. And then we have what happens if we choose the other half. So if we say x is less than 0, okay, the restriction, you can guess that the restriction for the inverse is going to be y is less than 0. And actually, it's going to be the other half of this parabola graph. And it's going to look something like this. Okay, it's not perfect. I think we can give up on trying to be perfect. Okay, so that's the reflection of this specific graph. So this is the y is equal to 3x squared, and then this would be the, let's keep it like that. Let's do this. This would be the y is equal to negative square root x over 3. And of course, the restriction is y is less than or equal to 0. Let's change this one to or equal to as well. Yep, the restriction there is y is less than or equal to 0. So I hope that makes sense. Let's try and do this. Okay, there we go. Okay, and if you care to remember, just to help you understand, here we have a little fish, and here we have a bird. Okay, so just remember the shapes of your graph. If you have to draw the regular and the inverse, you'd need a fish. Okay, if you're drawing something else, for example, if you had to draw this reflection and not this, this is not a fish or a bird, and there's something wrong. Okay, so let's have a look quickly. If we had negative x squared, so remember this is a, and this indicates a in a parabola indicates smiley face or sad face. Okay, so that's what's replicated here. Now we have sad face, and it's below the x-axis. So in that specific case, firstly, I'm going to draw the reflection. The reflection about the y is equal to x line would look something like, okay, let me just draw it freehand. Okay, it would look something like that again. Okay, sorry, one more, this is going to irk me. There we go, that's slightly better. Okay, so it would look something like that, and we can find the inverse. So let's quickly do it like really small here. If I had to find the inverse of this, I'm going to flip x and y. Okay, and then I have x over negative 3, which is equal to y squared, and then I square root both sides, and I have y is equal to, again, outside I have plus minus negative x over 3. Now you might be wondering, how can I take in the very first lesson that we did, I think, I'm not too sure. I think we maybe did like functions, algebra. And we said that whenever we have the square root of a negative, that's a non-real number. So you might be wondering, how can I take a square root of a negative number? Okay, that's simple because, okay, so here we have found what? We have found the equation of the inverse. So firstly, let's write it. So our equation here is y is equal to, am I going to take the negative or positive one? I am going to take the positive one because it's above the x-axis where the y values are positive. So it's positive square root of negative x over 3. Again, so why do we have a negative inside of a surd? How does that make sense? It's simply because every single possible x value for this pink graph is negative. Every single positive and every single possible x value for this pink graph is actually negative. So what you are going to be doing, you are going to be substituting a negative. So it's going to be negative x over 3, which then just simplifies to positive x over 3. Okay, and then you are not actually taking a square root of a negative. Okay, so just keep that in mind if that was confusing you, or if you didn't understand that, or if you're learning it, then hope you understand it. Okay, so yeah, it also helps to sort of like, instead of just memorizing it, you can understand this, and then when you're doing it in the question, it might make more sense. So let's do the final one. If I have to reflect this about the y is equal to x line, it would look something like that. Okay, and again, we have a little fish, very weird looking fish, but we don't care. And then, yeah, I don't know if birds have eyes. I don't want to do anything weird, but they're basically a bird and a fish again. Okay, so you need to sort of have that pattern. And in this case, okay, we have the formula y is equal to, we're going to choose the negative this time. Y is equal to negative square root negative x over 3. So again, this is going to become positive inside of the third. We know that because every x value again here is negative, and then you're going to have a negative. It's going to make the ultimate y value answer negative, and that makes sense because we can see that this whole entire graph is below the x-axis where the y values are actually negative. The restriction here was x is greater than or equal to 0 and x is less than or equal to 0. So the restriction for this one would be y is greater than or equal to 0. And then for this one, it would be y is less than or equal to 0. Okay, it's the same as the sort of the restriction on the regular function, but just instead of x, we use y. Okay, that might be a lot to take in. So just remember to go through it again afterwards to make sure that you understand, but let's move on. Okay, so we talked about inverse of straight line, we talked about inverse of parabola. Let's talk about inverse of hyperbola, and then we get to inverse of exponential. Inverse of hyperbola. Okay, so we're following the same concepts. Okay, so inverse of hyperbola. So we have the regular function and they want us to find the inverse. Again, nothing changes. So with any inverse, you're following the same steps, right? To calculate the equation of the inverse function, you're following those 3 steps that we learned in the start. Again, so I'm going to write it in standard form. I'm going to have y is equal to negative 5 over x plus 3 plus 1. Now, wherever I have x, I'm going to write y, and whenever I have y, I'm going to write x. Okay, and then I'm going to try and leave y alone. So it might, so sir, the negative root negative x. So someone is asking, this one here, the negative square root negative x, would it have no solution? No, it would have a solution. Okay, remember, we can't not have a solution because this is the correct equation for the graph. Okay, so if it is the correct equation for the graph, then every coordinate, okay, within the domain and within the range that you plug into this equation, okay, should be true for that graph. Meaning, if you substitute a equation, so when you substitute a value here, it should give you a corresponding y value. When you substitute a y value, it should give you a corresponding x value, okay, for the given range and domain. So I'll give you an example, right? Why it would give a solution, because the reason actually it would give a solution is because you can have a negative outside of a surd. There's nothing wrong with having a negative outside of a surd. Okay, so let's choose a value to substitute for x, and let's do a quick example, right? So for this one specifically, let's just say that here the coordinate is actually x is equal to -3, and let's plug that into our, or let's just use 9. No, yeah, no, yes, maybe, I don't know. Let's use 12. Let's just say this is pretty far back. And the coordinate here, not 12, sorry, -12. Okay, the x coordinate is -12. So let's solve for its y value. Y is equal to negative, open brackets, -12, because I substitute with brackets, over 3. And now let's simplify this. So the two negatives are actually going to cancel out. So I'm going to have negative outside of the surd, and then it's going to become positive 12 over 3. Negative outside of the bracket stays. 12 over 3 is actually 4. Okay. Negative square root 4 is actually 2. So your y coordinate is -2. So there's nothing wrong with having a negative outside of a surd. Okay, I hope that clarifies for you, and you may, and that makes sense to you and you understand. Okay, so the coordinate there would be -12 and -2 for this random coordinate that I chose. Okay, so again, having a negative inside of a surd, problem. Having a negative outside of a surd, perfectly okay, because you can take the square root of whatever is inside of the surd, provided it's positive, and then multiply it by the negative outside after you've taken the square root. Okay, let's continue here. So we were adjusting x and y. So I was saying it might look a bit difficult to do this, but it's really not that difficult. Just follow the same steps for hyperbola every time and you'll be fine. So the first thing you want to do is take over this value. Okay, if you remember correctly, this is actually the horizontal asymptote. It's actually the horizontal asymptote for the original equation. You take it over to the other side. So you have x minus 1 is equal to -5 over y plus 3. Then you take this over as multiplication, okay, because it's currently division on the right hand side. So when it goes to the left, it should become multiplication. So okay, so you have x minus 3, you have y plus 3 is equal to -5. Do not multiply this out. Okay, calm down, relax. Do not FOIL this. Okay, take the x minus 1 over to the other side, because these are like in multiplication. It's like two brackets multiplied by each other. So I can actually take, so I'm going to be left with y plus 3, and I can take this x minus 1 over to the right hand side as a division, the whole bracket. Okay, so I have -5 divided by x minus 1. Just give me 1 second, apologies. Okay, right. And now I need to leave y alone. Of course, that's my objective. So I can take the 3 over to the other side, and I will have y is equal to -5, this whole entire bracket, this whole entire fraction, -5 over x minus 1 minus 3. Okay. -5 over x minus 1 minus 3. And you'll notice that the inverse of a hyperbola is actually a hyperbola again. Okay. And we have a little note here that says that, which makes sense, by the way. Remember, the vertical asymptote has an x coordinate and the horizontal asymptote has a y coordinate. So from the regular function to the inverse function, the vertical asymptote actually becomes the horizontal asymptote. So let's do an example. If the vertical asymptote is x is equal to 1, the horizontal asymptote on the inverse is y is equal to 1. If the horizontal asymptote on the regular function is y is equal to -3, okay, the vertical asymptote on the inverse is x is equal to -3. Okay, don't make a confusion and then like make it +3 or something. Okay, no, it's the same exact coordinate, just instead of being y, it will be x, and if it was an x, it would become a y. Okay, and that's actually proven, okay, with the equations. If we have to look at these equations carefully, okay, not that carefully, we can just look at them. These two coordinates are special. Why? Because this is actually the vertical asymptote, and its equation is x is equal to -3. Okay, you should remember this from hyperbola. Why -3? Remember the x values. The vertical asymptote always takes the opposite sign to what it is in the equation. And this guy is our horizontal asymptote, and its equation is y is equal to +1. Horizontal asymptote keeps the same sign. Let's compare that to this guy. What is this guy? This guy is our inverse. So this is for our regular function. Let's compare it for our inverse. In our inverse, we can see that, let's highlight it. We can see that this is our vertical asymptote, and it has the equation of x is equal to +1, opposite sign, remember. And this is our horizontal asymptote, and it has the equation y is equal to -3. Same sign. And if you notice, you will see that the vertical asymptote became the horizontal asymptote, and the horizontal asymptote became the vertical asymptote. So you could also just simply use your understanding of that and rewrite the equation with your understanding of vertical and horizontal asymptotes. Hello to the person who said hi in the YouTube chat. Okay, so let's move on quickly. Let us just start this, and then we can finish this up next week with all the different graphs. But let us at least learn the basics of exponential. Or should we? Okay, let's end a bit early. Okay, and let's continue next week. We'll start rather fresh with the inverse of exponential. Okay. Okay, if there's, you guys can ask some questions. I'll give you guys like 1 or 2 minutes to ask some questions. So yeah, we finished up till inverse of hyperbola. Hope that everything makes sense. Next week we'll continue with inverse of exponential. We'll do some questions, and then we should be done. And then we'll be moving on to, I believe, Euclidean, I think, Euclidean geometry. Yes, Euclidean geometry, which is the most fun topic ever. I think everyone can agree. When will we get to do trigonometry? Oh, sorry. Yes, you are correct. We're actually going to do trig before we do Euclidean. Trig is still a term 1 topic. So obviously we're a bit slow, a bit behind, but I believe that we can catch up. If we just persevere and push through, we'll be able to catch up. It's just that, yeah, functions, I think, took a very long time. Okay, but I hope that it was beneficial and that you guys can understand, because I would prefer you guys have a good understanding than we just rush through everything. But yeah, actually we'll do trigonometry and then we will do Euclidean. Okay, but if there are no further questions, then yeah, just a reminder, because we're back after a very long time, and maybe for those of you who are joining us for the first time, that whenever you have any questions during the lessons, you can feel free to put them in the YouTube and the Q&A or the chat. I know it's a bit late for that, but yes, okay. Just remember that. Remember that the document that we do, all the notes that we do, is uploaded to the Google Drive. The Google Drive, a link for the Google Drive can be found in the group description. Okay. And the video, the recording of the lesson, will be uploaded to YouTube as well for you to watch afterwards if you want to rewatch it or get an explanation again or something. When will we cover calculus? We will do trigonometry Euclidean geometry, analytical geometry, and then calculus. Okay, let's just see if you guys really want to, because you've been doing analytical and Euclidean for, this is the second year. If you guys want, I can start with calculus. Maybe I'll put up a poll in the group, and then I can start with calculus. Okay, so immediately after trigonometry, maybe we can start with calculus. Okay, and then we can move on to Euclidean and analytical. So yeah, I think I'll definitely do that and see what everyone thinks. But yeah, okay, that's it for this week. I will see you guys next week. Thank you guys so much for joining. Have a good week of school, and we'll meet again next week. Jazakallah khair. Thank you guys so much.